In physics, it is often useful to describe things as vectors or vector fields, and in doing this we often use the Nabla operator, which is also called del, to perform the three operations gradient, divergence, and curl. Gradient yields a vector result, which is called the directional derivative, and this can be thought of as almost the three-dimensional slope of a field. Divergence will yield a scalar result and can most simply be thought of as the rate at which stuff leaves a given region of space. So it's also called flux, which might be easier to understand. So it's the net rate at which things leave and exit a given space. So for example, in the case of a magnetic field, the divergence will always be zero because magnets are dipoles, so they attract and repel the same amount of stuff, and thus there's no net increase or decrease in the amount of magnetism entering a magnetic field. The curl operator outputs a vector result, and this is simply thought of as mathematically the rotation of a vector field, and in physics it's useful for describing angular momentum and rotation of different fields or objects in space. Each of these operations has in common the del operator or the Nabla operator, which by itself is meaningless because these partial derivatives are not applied to any function or any vector components, but is extremely useful for expressing gradient, curl, and divergence. Just a quick review of partial derivatives. If you have the function f of xy z equals x squared y plus 3yz plus z squared, then the partial derivative with respect to x will so what you do when you take this is you treat x as the only variable and you'll treat y and z as constants. So the solution to the partial derivative of f with respect to x would equal 2x y plus 0 plus 0, because yz and z squared are constants in this case. The partial derivative of f with respect to y, in this case you would treat y as the only variable and x and z as constants, so you would have x squared plus 3z plus 0. And for the partial derivative with respect to z, you treat z as the only variable and x and y as constants, so you have 0 plus 3y plus 2z. For the purpose of this lesson, I'm assuming that you already know how to take a derivative. For gradient, if we are given the vector a, b, c in terms of x, y, and z, the Nabla operator is applied directly to the vector and is written as such, and this will equal a vector solution of partial A partial x, partial B partial y, and partial C partial z. So for gradient, you simply take the partial with respect to x of the I component, the partial with respect to y of the j component, and the partial with respect to z of the k component to give you the directional derivative. To mathematically describe divergence, we will again use the vector v with components a, b, and c in terms of the variables x, y, and z, and the del operator. Divergence is denoted as del dot the vector, and I'm assuming that you all know how to do a dot product, but just for review, if you have two vectors, say the vector A with components, we'll just use two variables for brevity's sake. If you have the vector A, which is defined by the components A1, A2, and B, defined by B1 and B2, then A dot B will give a numerical result, which is not a vector, and to do this you multiply the first component, the first two components, and the second two components, and you add these together. And if there were three components, you would also add the third component, the product of the third components. So you have A1 B1 plus A2 B2. So for divergence, we don't multiply the components because the del operator's components have no meaning without being applied to a vector. Rather, we apply the partial derivatives into the vector and add up those components. So we have partial A partial x plus partial B partial y plus partial C partial z. So this is very similar to the way the dot product looks, except instead of multiplying the partial derivatives which have no meaning by the components A, B, and C, we apply the partial and add up those components. We will again use del and the vector v equals ABC with variables x, y, and z to describe curl, as we did for divergence and gradient. Curl is denoted as del cross the vector v, and to review, the cross product of vectors with three components, so let's say you have vector A equals A1, B1, A1, A2, and A3, and the vector B equals B1, B2, and B3, then A cross B can be defined as the determinant of the matrix I, J, K, where you write out the components, make sure that the order is correct, and to do a matrix with 3 components for vectors. First, you do the j and k components, so you'll do a2 times b3 minus a3 times b2 I minus, because the j component will always be negative, so minus a1 times b3 minus a3 times b1 j plus the k component, which will be a1 b2 minus a2 b1. Okay. Now, I'm going to assume that all of you already know this, so that'll just be a quick review of how to take the cross product of 2 3 vectors. And similarly to what we did with the with divergence, when we apply del, we don't multiply it in the cross product, but we apply the partial derivatives, and this isn't erasing for some reason, but we apply the partial derivatives and then take the cross product. So del cross v will equal the determinant of the matrix I, j, k are your components as you write them in, delta x, delta y, partial z, a, b, c. So to write this out, you'll have, for the first I component, partial c, partial y, minus partial b, partial z, I, and you'll see that that's because we apply that to c, and we apply that to b, minus, actually in this case it's plus because the del operator cancels out the negative for j, partial c, partial x, partial a, partial z, j, plus partial b, partial x, minus partial a, partial y. So that's how you do curl. It's the cross product of del and your vector, and will yield a vector result. I won't go into this much, but there are other operators which are very similar to the Nabla operator, one of which is the Laplace operator, which can be written as del dot del, del squared, or a capital delta, but I don't often use the capital delta because that's too similar to the symbol for change. So this operator, the Laplacian, is simply the gradient, and it's the gradient of the gradient, so it's the second partial derivatives, written out the same way with the same components, but you won't generally see this in your multivariable class. And you also won't generally see this operator, which is the D'Alembert operator. And this is primarily used for special relativity, and it's the divergence, or the Laplace operator, of Minkowski space. And so it's in tensor form, which I also won't get into. This is just a brief introduction in case you want to learn more about this. In tensor form, this is written as delta with the superscript mu, delta subscript mu, and this is written out as gradient 1 over c squared, where c is the speed of light, partial t squared, with second derivatives minus the Laplacian operator. And like I said, you won't see these much, and the D'Alembert is mostly used for four-dimensional physics. Thanks for watching. I hope through this video you were able to better understand some simple vector calculus and get a better grade on your multivariable test.